is there. I have shared, I'm going to share the link for the academic free master. So all of you need to just create a login, and once you create a login, then you will be able to download this free visualizer. But none of the calculation, anything that you have to do on calculation front, it won't work. So that is the thing. So Prajwal, any update on the file? Hello.
Yeah, it is
Hello.
still being uploaded.
Okay, great. Anybody else have any other questions? So we can address that in the meantime. So nobody have any questions, doubt? We have a crowd of participants, size of 74. Video of the yes, there are many videos available, and yes, this recording also I'm ready to share. It will end up being quite a long hours, but yes, I'll share it. Please write to me. Can you elaborate on protein selection criteria, particularly RMSD value? Prajwal, like, would you want to add something on that?
Yes,
Hello.
yes. Yeah.
So
So there
Dr.
are
Bharat has asked, sorry, Prajwal, I'll just finish this part. Which login ID used for the download? Nothing, just you have to click the link maestro, free maestro, which I have shared. It will ask for a login. You have to create a login. Once you create login, it will already have pre-installed license. Yeah, thank you, Prajwal. Please go ahead.
Yep. So for protein selection, there are various aspects which you need to look for, and those are like protein name, its organism, from where it is extracted. Then you can also look for its resolution, how many number of residues present in it. Ideally, there should not be any missing residue. Then you can also look for the parameters like inhibitor structure which is present inside the protein, how much its biological activity is, better the activity, better the structure is. So these are the aspects which you need to look for in terms of protein selection. So particularly RMSD value, when you talk about in protein selection, so RMSD value is always with respect to some reference. So I think RMSD value comes into picture when you want to compare two similar proteins. But in general, if you want to select a target protein, so these are the previously mentioned criteria.
Thank you, Prajwal. I think there's another interesting question. The pre-share protein structure loop refinement homology modeling, VALD. Could you please elaborate? Doesn't it seems like a topic for some abstract submission? If the name is user, please could you please elaborate your question? Prajwal, like, is the data back?
Yes, data is back. So
Okay, great. I think we can resume. Thank you.
yeah, let me share this. So here you go. Yeah, so I hope the screen is visible now. And as I said, you can see on everybody's desktop, there is a folder called data. So you can see this is the data directory which is present for everybody. And this is what we have created a directory, and you can see there is small lock appeared on it. It means this is the protected directory, right? Protected directory. So you can't write anything inside that, but you can use all the files inside that data folder. So if you go inside the data folder, you'll see there are number of folders which are present, and all those are necessary for this workshop. So for example, the folder name called MTP workshop file is the folder of our interest. Inside that, whatever files are there, we are going to use it today. So if you double click on this MTP folder, you will see there are number of files, and out of which the file of our interest at this point is this input ligand.se. So this is how I have shown you like where the files are. but I'm going to import the same file using Maestro. So I just close this and let's go to Maestro now. So here you go, carefully take a look. So I have opened the Maestro now. In Maestro, I need to go to File, Import Structures. This is the option to import the structure. Again, don't try to remember, it is all present inside the handouts mentioned. You just need to follow it correctly. So in import panel, you see it automatically directs you to the working directory. You just need to go to user, home user in drop down. You see the desktop folder, double click on the desktop folder. You will see the data folder. Double click on the data folder and you will see the folder name called MTB workshop file. So this folder is very particular. You need to make sure that you are following correct folder, MTB workshop files. So just double click on that and you will find number of files, out of which the file of our interest is ligand, input ligands.smi. So this is what the input ligand file which I have downloaded it from database and kept it for ready to use for you. So you just need to select that particular input ligand.smi file and say open. So at the bottom, there is a open button. Just click on open and you will see all the ligands are loaded. So there are number of ligands which are present inside the this particular file and all are loaded. So as these are the downloaded ligands in Smiles notation, so these are only 2D structure of molecules which are present. You can go through all the structures one by one and see these molecules are not in 3D, but only in 2D. There are no hydrogen present in this structure. There is no energy minimized conformation. So you need to basically make it correct all one by one, but to do all those things automatically, so as you can see, there are number of ligands which are present in the file. So it is cumbersome to do all the refinement of the structure, each and every molecule one by one. So this is not a suggested thing to do. So what you need to do here is you just need to go to ligand preparation panel and prepare all the structures in just a single click. So for that, you just need to go to task, then browse, and in browse you find at left side you will find the option called lig prep. So lig prep stands for ligand preparation. Just click on that lig prep and it will open a straightforward panel for you where you just need to provide your structures from so if you see the drop down, you will see you can provide structures from workspace, from project table, or from file. The by default it says use structure from file, and just below that you will see there is a browse button. Do not get confused. There are two browse buttons, but always you need to remember you need to look into browse button just below this first option file. Click on that browse. Now I request you to go to that same folder which we have just now seen, like which is in home user. Then on your desktop, if you go inside that, there is a data folder. Inside that data folder, there is a folder called MTB workshop file. And inside that, you will see that input ligand.smi. This is the same file which we have loaded on screen. And now we are providing the same file in lig prep panel. Just select that file and say open, and you will suddenly see the complete path of this ligand file is given here. It means the input file is specified. All the options you can keep it as default. For example, generation of various ionization state, generation of tautomers, generation of various stereoisomers, and all. What at most you can do is, if you want to save your time, you can generate at most one per ligand. So there is a number, it will generate at most 32 structures per ligand. So you can limit that number to, let's say, one, just to save your time. I request you to do that, change that number from 32 to 1, and that's it. That's the only thing. And the same thing is also mentioned in the handout. Just try to follow the handouts correctly. Now, before hitting run button, again, I am saying same thing. Go to this bar bin, which is called a job setting. Click on that. Change the host from local host to CPU 320 so that your job runs faster on cloud. You can also parallelize your job on number of CPUs if you want. For example, default is one processor. I just make it to 5 processor. And that's it. You can click on run and it will submit the job. You can see it says the submitting job and soon it will start running. So the status is job started. You can also monitor the job in job monitor button. You can see the current status of job is rating. I think it may take 1 minute to complete this job once it start running. So this is what the only thing which you need to do it. Try to follow the handouts correctly and let us know if you come across any questions, any queries. So we can have 5 minutes of wait for submitting this job. Just check the Zoom chat box. I have shared with you the link for handouts. So go to the handout, try to do it exactly, and let us know if you have any issues. Thank you very much.
Yes, I hope all of your lick prep is done. May I know if anybody can just confirm me the status. Do you need more time? If you need more time, let me know. I can see three duns. Still running. Okay. Dear participants, so I think I can see that many of you have said the job is done. So I will share my screen and proceed further. I greatly appreciate your patience because post lenses are quite sedative in nature, and we have successfully crossed that part. So all of you enjoyed that, right? Like so, right from morning, you just saw how we slowly started. We took molecules, and then we prepared the protein that is 6B2Q, and then Prajal showed you how to prepare it, and then set it up for grid generation, and then he imported around 36 molecules and performed leak prep for the same. So you could see here the default launch will somehow generate around 96 because of the stereoisomers, ionization states, and other informations. So this is the output it looks like, and you can see the 3D structures, and you will be able to visualize the same in 2D in this 2D viewer also. So you can see all the structures. And now it is our responsibility to cross check as among this, which is the best molecule to proceed for further for biological activity. So this is a collection of molecules. We're not just talking single molecule, a collection of molecules, and that is going to be done by using Glide software. So here you can see Browse has many software. As for morning, we saw many tools, and you can see here there is option for glide and then ligand docking. So here is the option, and we are supposed to click browse. So it is going to show you in your working directory glide grid underscore one dot zip. So here is a zip file which has been uploaded, and this is basically where to dock. Where to dock is the information where you define the receptor, which is in the form of zip file. Then what to dock? What to dock is the ligand molecules, right? So we will try to dock the lig prep one out.magz. So that is the file which I have took. So this is what to dock, and this is where to dock. Now the third aspect comes is how to dock. So basically, as explained in the morning, the presentation, there are three modes of docking: high throughput virtual screening mode, then standard precision mode, and extra precision mode. We'll try to run the calculation in standard precision because we tentatively have close to 100 molecules in a flexible ligand is going to be flexible, whereas the ligand, the protein will be rigid in nature because this is molecular docking. Okay, rigid molecular docking. Protein is rigid and ligand is flexible. So SP suffix, I'm going to give 6B2Q. So that's all you need to mention the standard precision, browse the ligand, the grid, and we are all set to perform the docking so that we shortlist them. So please make sure you go for CPU, and then I'm going to give you 8 processors so that my calculation runs faster. Okay, and then go ahead and run. It's as easy as that. Our overall objective is to identify which molecule is the best and why it is best. So I request all participants to launch the calculation and let me know if any of you face any difficulty. So here you go. So we have, I will just check. I'm going to share you the handouts for launching the job. It's pretty straightforward. So here is the handout for launching the docking submission. So I request all of you to launch the job. If anybody faces any issues, please let me know. Thank you. Do you have any questions? You can raise it now. Otherwise, you can follow the handout and launch the calculation. Dear Dr. Sandesh, if you have missed the grid generation, you can browse it in the data folder, the same where you have browsed the lick prep out file. In the same location, you can see the zip file is there. That you can use it. So it seems I think my calculation is over. Yeah. Anybody else who has launched the calculation? So I can see. So I'm going to wait for another 5 minutes. Yeah, I'm sharing the handout again. Dear participants, welcome back. I just want to check if I'm allowed to proceed. May I know if the status of the job is over for most of you? Are any of you facing any issue or difficulty in just still running? So if most of you say yes, then I can start the analysis. And in the meantime, the job will be over. If you allow, if all of you permit, then I'll be able to proceed. Okay, in the meantime, I have a poll which I felt like taking. So this poll is on leak prep. I request all participants to participate in a poll. Thank you for participating in the poll. Can I prepare organometallic compounds using leak prep? The answer is no, but most of you have said the answer is yes. I'm going to share the results. You cannot prepare organometallic compounds using leak prep. You need to use Jaguar quantum optimizations, and then only you will be able to proceed further. Okay. So no, I think I can proceed further. I shall proceed further with the analysis. So, what is the objective behind doing the whole study? The objective was to shortlist molecules which are qualitatively and quantitatively the best against the target of interest. So, you can see here, let me try to share the screen. So, here is the screen shared. So, hope you are able to see my screen now. Now, you'll see once the result comes, glide dog sp underscore 6b2q. Here you can see a small tree graph is there, like a small bar diagram will be there. If you click that, you have to click on view poses. Automatically, the view will be set in such a way that the ligand will be visible. Still, if it is not visible, if you're facing difficulty, just double click on this preset. Okay, just click this and say apply custom preset. So here you go, you can see the ligand is there and the protein is there. You can hide the ribbons for better clarity. So this is first we will see qualitatively and then we will try to quantify the overall analysis. You can check with the ligand interaction diagram in the left side where you can see here ligand interaction diagram is there. So if you, this is 3D and that is 2D interaction diagram. So you get to see the explanation of the overall interaction, and this image also can be saved as an image also. In case you want to do the same in 3D, you just saw the best and quick option is to do this preset and then apply custom preset. Okay, so if you do that, you can see the pose ready to be visualized. In similar manner, make sure you activate like one by one pose because there are many molecules docked and we are here to evaluate. Okay, you can see just click this and hit preset, then immediately you can see the best view possible. So here it is, just click and apply custom preset. So like that, you can change the poses of because if docking is going to give you one among the best pose. If you're interested in more poses, that also you can mention it in the docking analysis. Let me just try. Now, usually molecule can be purely selected based upon non-bonding interaction. It can also be purely selected based upon docking score also. Now, in case if you decide my molecule should make this three key interaction, only those molecules I'm going to select. That is that also you can do. So you need to compare this interaction with the native bound interaction and take a call whether the molecule will be good enough to proceed further. The other way people do is generate the molecular surface of the protein, and by that also they visualize how well the protein has been bound. So this is qualitative analysis, which has to be done manually. Quantify is all the options are pretty straightforward, but try to compare with always with a native molecule. In this case, we have not docked, but you can analyze. These are all derivatives. You can decide as which molecule is the best. Now I'm going to generate the molecular surface for only protein. Then I'm supposed to evaluate the orientation of the ligand molecule. I don't know. I think my instance is little slow. Yeah. So I will try to show you. You remember the molecular surface part, right? So let me just try to show you. So we are supposed to visualize it as how the orientation of our native molecule is and how is the orientation of the ligand molecules. And accordingly, we have to decide whether the pose is properly saturating the binding pocket or not. So like that also you can select the molecule. You can also select the molecule based upon non-bonding interaction parameters, and one among them is glide docking score. Or you can see like you have Autodoc Vena score, or they have everybody have their own scoring algorithm. But if you see Glide uses chem score approach for scoring the conformation, and it has the docking score is a summation of all the non-bonding parameters. So let me just try to show the values, but I don't know, it's very slow now. So I'm just refreshing it because the instance was too slow. I don't know what happened. I don't know. In the meantime, I think you can do the analysis. I'll just show you the quantitative values also. I think it's just loading. So basically, you can select the molecule based upon non-bonding interaction, the pose orientation, or the size of your molecule also. So that is just by visual inspection. The second way is by using scoring approaches, like which will be listed in the project table. So let me just wait and show it to you. Okay, in the meantime, I don't have much options but to show the docking analysis. Okay, that's a handouts. You give a try. I think if the result is over, then it's easy for you. In the meantime, okay, I can see Mukti Jadhav has asked. So mostly glide score and docking score is same. Uh, but if you see epic state penalty is the what is subtracted from the glide score. And docking score, I think, does not have it. So there is epic state penalties which is caused for the ionization states of the molecules. So I've shared the docking analysis. Once that comes, then I will be able to show it. But in the meantime, you can others can try it out. Anybody else have any other questions? So in the project table, we can see the complete docking score and the other sub scorings. I don't know. Is it all your instance are freeze like this? Yeah, there is another question which was raised by Mukti. So using prime mmGBSA, we can calculate the binding free energy. So here, I think my machine came back. So you can see here the project table has the complete scoring. So usually scoring is the one which uses to rank order the different molecules. But you can subcategorize it and have other parameter also to shortlist the molecules. You don't have to just stick to docking score alone. So I'm just gonna show you only the docking parameters. I have unchecked it. It's a property tree. You can click on this glide. Let me just try to. So here is the complete docking output. And usually we need to scroll down to see the docking score. So scroll to the bottom and then here you can see the docking scores. The XYZ coordinate is also mentioned here. You can see this is the XYZ coordinate used during docking. And if you slightly drag to the right, we can see docking score and other scores. It's like an Excel bar. because the system is quite slow, so I'm facing difficulty in visualizing it, showing it to you. Okay, so let me just use, yeah. So here is the docking score, you can see. So more the negative, better it is. And in case if you're interested with important secondary properties like energy, Coulombic interaction, van der Waals, hydrogen bond in specific, all those options are also there. And if you want to summarize overall interactions of all the molecule that you have docked, we have a tool called as SIFT, SIFT. Okay, this is going to summarize the overall interactions against the protein of interaction, all of them. Okay, all the poses will be considered, and it is going to generate a display interaction matrix by which we can decide how the molecules are. It's like residue based analysis. You can see overall residues are in the x-axis, y-axis has all the ligands, and in the top it has the ligand counts, residues, and here it is the count of the ligand interactions. So as per the non-bonding interactions, you can distribute this to backbone interactions, you can navigate to polar residues, all those things you can explore. So I think I have already shared the handout. So I request all of you to take time. So this is very, very crucial. And if you have any questions, please feel to ask me. And as per Mukti Jadhav, the MMGBSA value is here you can see in prime MMGBSA is there. So this will calculate the binding energy, free energy for your docking protein ligand docking complex. Anybody else have any other questions? No, Jairaj, I think it is restricted. So are you talking about this cloud instance? Yeah, no, sorry. I think one of the participants is requesting if they can get 24 hours. You can download the interface, you can take a evaluation. So those things are possible, but I think by today night they will close it. It is 1 day workshop only. Or you can collaborate with the LM College of Pharmacy also. They currently have the license. Anybody else have any other questions? So you just saw like right how tricky it is like for molecules because this was similar kind of derivative. We docked it. So we have a very recent tool which is quite handy to be used, and that is called as ligand designer. So I think I can call upon Dr. Kaushik if all of you don't have any questions with the current discussions. Uh, how you can do collaboration with other university PhD students. Uh, Titi Trivedi. Now, if you're our customers, yeah, I'm always available. I'm always collaborating with all the customers. So, or else I motivate others to collaborate with yeah, the other customers. So just write to us, and accordingly we will help you out. So who has shared the screen? Is it Kaushik? No, Krishna. Krishna, do you have anything to show? Krishna, please stop the screen share. I can see that you're doing a great job. Yes, Kaushik. Kaushik?
Yeah. Uh, can you hear me?
Yeah, I can hear you, Kaushik. Please help us with this session on ligand designer.
Yeah, just give me 1 minute.
Krishna, please stop the screen share. Krishna Pathades. Yeah, thank you.
Okay, so just hold on. And there, right. Can you see my screen, Vinod?
Yes, I can see your screen.
Thank you. All right. So, thank you, Vinod. Thanks everyone for staying till now. Vinod, can you mute your mic? I'm feeling the echo. Yeah, thank you. Right. So what we have done since morning, just as a recap, is that we have seen how to sketch molecules. We have seen how to see the protein structure, how to visualize the protein structure, and things like that. And we also, like, after that, we have prepared the protein. Then we have imported some molecules. We have prepared the ligand molecules. Then after we build the grid to identify the binding pocket, then we did the docking calculation, and we also looked at the results, right? So this is all well and good. But what if the ligands that you have chosen in your initial data set are not good enough to interact with your protein? All right. So in those situations, you'll have to modify the ligand molecule further to make sure you have more interactions with your protein. So what we're going to take a look at right now is how can you modify the molecule and what tools do you have to make sure you can maximize the number of interactions between the ligand and the protein, and also get to know the ADME properties of the molecule. Sorry. Yeah, there. And just hold on. Okay. Right. So to do that, what you would need is, so you actually, like, the idea behind this thing is that you have a decent molecule, but it's not the best molecule. So you want to make it from a decent molecule to a very good molecule. And so for that, since you have done the docking calculation, what we can do is we can try to, like, let's say, include this particular protein in the workspace that we have already, like, got the docking results here. And for the same protein, let me also, like, turn on the ribbon so that I have a clear view of the protein. Thank you. That's good. Right. So this is the protein here. And I'm going to also include one of the ligands from this particular docking result here. So you can see that the two circles are blue in color, which means now that if I take a look at my workspace, I have both the ligand molecule and I also have the protein molecule. And also, like, let me just hide the sequence at the bottom. I don't need the sequence viewer. So I'll just want to focus on the protein here. I'll also remove the studio overlay here. I can just go to window here and remove the stick in front of it. Right. So in schrodinger, we have a single tool which can be used for optimizing your molecule once you have the initial good molecule. So the tool for that is you can go to task here, go to browse here. And once you go to browse, then you go to lead optimization here. Okay. In lead optimization, once you click on that, you have a tool called ligand designer that is available to you here. And once you click on that particular option, it's going to open a panel on the right side. And for this tool to work, you need to have a receptor ligand complex. You can't have just a receptor. You can't have just the ligand. You need to have both of them. And so that's the reason why I made sure that the circles are blue in color for both the protein and also one of the ligands here. And once you have got that thing, you just click on Analyze Workspace, and this will just take, like, just a few seconds for it to analyze. It's going to give us quite a few information that will be very handy in trying to optimize your particular molecule. Let me adjust my screen. Okay. I'm not sure why it is shifted to the right. Good. So let me maximize it. Okay, never mind. We try to work with this setup here. Right. Okay, that's good. Now it's maximized. So if you take a look at this particular view right now, what you'll see is that in this particular workspace, you have different colors available to you here. So you have the dark blue color, which indicates the solvent exposed part of the protein. The text is not clearly visible here, but if you see this, if when you run the calculation on your own machines, you'll be able to see the color codes that are listed here, where you have like light blue color is for cavity, dark blue color is for solvent exposed regions, red is ugly clash, and orange is bad clash. So if you take a look at this molecule here, you can see that this part is dark blue in color, which means that this part of the molecule is solvent exposed. So any changes that you're going to make to this molecule, if you make these changes in this side here, they will not benefit the interaction between the protein and the ligand because there is no protein on this side of the molecule. The protein is only present on the other side of the molecule where there is not solvent exposed regions. So on this side here, if you take a look at this, you have the light blue cloud, and the light blue cloud indicates that there is a gap between the ligand and the protein in which you can try to fill your atoms. So if you have a gap between the ligand and the protein, that means there is room for improvement of your molecule to interact better with the protein. So if you want to find out which atoms or the protein are in this side of the molecule, you can click on this option called ligand receptor interactions here. And once you do that, it's in the same panel of ligand designer. You can see that the amino acids of the protein in the binding pocket are getting displayed here. So, and if you also see here, you can see some of these yellow dots here. These are the interactions that you looked at before when you did the docking analysis. There is one hydrogen bond here, one more here, one more here, and probably you have one more also here. And so you have quite a few interactions. You can also see the type of amino acid you have. You have a donor, you have an acceptor, you have hydrophobic amino acid. And if you put your cursor on any one of these particular side chains, these amino acids here, you can see which atom of the amino acid is facing the ligand molecule. And if it's a backbone, if it's a side chain, you can see all the information in one single panel here. So this is quite useful information. Now that you have this data here, you can see exactly how the binding pocket is shaped. You can see which atoms of the ligand are interacting with the protein and which atoms are not interacting with the protein. So for example, we have focused on the hydrogen bond interactions here. If you also take a look at this region here, you have a cyclopropane group here. And that cyclopropyl group, like the cyclopropane group, is going to interact with these hydrophobic groups here. And that is going to give it hydrophobic packing that is also critical for the stability of your molecule. And if you also see this molecule here, you can maybe, we might be able to form an interaction with this acceptor here. That is one possible solution for us to make the molecule even more potent than what it is right now. Keep in mind that it's easier to change the ligand than to change the protein. So if you know that the protein has an acceptor here, you might be able to do a change in the group of the ligand here to see if it can form an interaction with this acceptor or not. And furthermore, if you take a look at this panel here, it's not just the interactions, it's not just that it tells you which part is solvent exposed, which part has the protein cavity and protein atoms here. What you also get in this particular software is that, in this particular panel is that, if you turn off the ligand is interactions, if you also turn off the growth space is the one that gives you the blue colors here. So if you turn the growth space also off, now you just have the ligand molecule. Now you can take a look at the ligand surface. So you can turn the ligand surface on, and now you see that you have green colored surface, red color regions, and blue color regions on the surface here. So the green colored region is the hydrophobic part of your molecule. The red color region is a acceptor, hydrogen bond acceptor in your ligand molecule. And the blue color region is a hydrogen bond donor in your molecule. So this is for the ligand. You can try to rotate the molecule in different directions. You can see how the molecule is shaped and all of those things. And what you can also do is, if I turn off the ligand surface, And if I turn on the receptor surface, so now you can see that it's showing the receptor surface. Again, the same color coding applies. Green indicates hydrophobic part, red is acceptor, and blue is donor. And now if you take a look at this molecule, you can appreciate how well the ligand goes and sits in this narrow groove in the binding pocket, right? So for example, it's waiting for the mouse to load. Right. Now if you take a look at this here, it's zoomed in too much. Just hold on. Yeah. So I hope now you can appreciate how well the ligand fits in this narrow binding pocket inside the protein. Okay. So this is information that you can get. Now you can find out how you can modify the molecule further to make it better. You can see that if you have an acceptor in the protein, then you want to have a donor in your molecule as well, and things like that that can be visualized also. And furthermore, in the same panel here, you can also see that there is something called a multi-parameter optimization, which has like a pentagon here. And the vertices of the pentagon is, one of them is log P, which tells you how soluble your molecule is going to be. Then you have polar surface area, you have hydrogen bond donor, hydrogen bond acceptor, you have molecular weight. So if you are aware of Lipinski rule of 5, Lipinski rule of 5 says that the number of donors, the number of acceptors, the molecular weight, and log P should be multiples of 5, and they have different ranges for it. So you can see that where this molecule falls particularly, you can see that log P is 2.3 for this molecule, and the recommended range should be from 0 to 5. The number of donors is 3, the recommended range is 0 to 5. The acceptors are 7, and the recommended range is 0 to 10. And you can also see the molecular weight and the polar surface area. And it also gives you something called the MPO, which is a multi-parameter optimization, which tells you how good a molecule is to be a lead molecule on a scale of 0 to 1. 1 indicates it's a very good molecule, and 0 indicates it's a very poor molecule. And furthermore, if you click on the settings option here, and you can also change this scoring function here, you want to have Lipinski, you want to have a different scoring function. You can try to do those things easily from here. You can even add more properties also. For example, you have 5 properties. If you add something like this one, now you can see that this particular thing became a hexagon. And now if I click on one more, it's a heptagon. If I click on one more, it's going to be an octagon. And that is the highest dimension you can go to. You can't go to 9 dimensions, things like that. So I'm going to remove those extra things that I added. So I'll just make sure I uncheck them and make it back to a pentagon, which is easier for us to interpret and understand, because the properties are very well known in terms of what the molecular weight should be and what these numbers should be for your molecule. And you have the vertices here. You can see where your molecule falls in this particular pentagon here. And you should not have any points crossing these vertices on any of these on this particular polygon. Okay. So now that we have seen that this particular molecule satisfies the properties very well, and you also know what type of where the growth space is for the molecule, you can see you have the dark blue region, which is not useful for us to make modifications. We want to make changes in the light blue region, and that is what we're going to focus on right now. And we are also going to turn on the ligand receptor interactions in this particular option here to see all the amino acids of the protein in the binding pocket. And once we have got this, in this particular scenario, there is not much room for improvement. Just hold on. Thank you. Right. So in this particular molecule, it's already very good molecules. There's not much room for improvement, but in some scenarios, we might have a decent chance for improvement. So if you see this particular thing, I'm not really sure if I can find any good spots here. Maybe I could try to form, to keep things simple, I'll just for the sake of exercise, I'll try to form an interaction with this particular acceptor here. Okay, it's a bit far from this particular group here, and I'm also not sure about the synthetic feasibility of trying to have a substitution on a cyclic cyclopropane group here. So but we're going to try it out. I just want to show you as an example as to how you can modify the molecule. In this case, it's not an ideal example, but in the future, if you're working on your own projects, you might be able to use this tool to modify your molecules to make it more potent. So to modify the molecule, what you can do is you click on the workflow option here. And this workflow, you can see that you have an option to attach an R group. So if you have a molecule, if you want to add a group here, you can attach an R group in this particular place. If you want to fill the growth space, for example, you have this particular light blue cloud here where you can grow your molecule, and that also you can choose options here. You have options for bioassociated replacement, and bioassociates are those groups that will have the same biological activity, but will have different ADME profiles to make sure your molecule has like better profiles in terms of pharmacokinetics issues. The same thing for associated scanning. Sometimes if you are dealing with water molecules, you might be able to like displace or replace water molecules, but this requires a separate tool that is we're not going to discuss right now. You can also try to form a ligand receptor interaction. That's also possible. You can cyclize your ligand molecule, or you can manually edit your molecule and see how the molecule will fit in the binding pocket here by doing this 2D 3D editing. What I'm going to do right now is, for the sake of exercise, I'm just going to choose attach R group. And once I do that, you can see that it's asking me to pick an attachment bond on the molecule. So I'll probably like pick this one here. And when I do that, you can see there's a yellow colored arrow that forms on that particular hydrogen atom. And once I got that, I can click on, you can see there's an option to enumerate here. If you click on the settings option here, you can choose what you want to replace this particular hydrogen with. So in this example, I want to form an interaction with this acceptor here. So I would ideally want to like make changes here that can form a hydrogen bond with this acceptor. So if you, once you click on the settings option here, this wheel here, it's going to open this particular R group library. And here you can go to the custom option here, and you have like different groups that are already pre-built into the software that you can try to substitute your molecule with and see if those substitutions make a big difference in terms of the potency of the molecule with your particular protein. So you can see that they have groups called E molecules that has around 2098 different fragments that are going to be substituted in the particular region to see if they're going to be better or not. You can use diverse R groups. You can use solving R groups. This is quite handy when you want to like maximize, when you want to like try to find all possible heat molecules for your particular protein. This is better. The solid-basic groups are better when you want to make sure that the molecule has like better solubility, better log p values, things like that. If you also take a look at it, you can see that we have groups for displacing water molecules, for forming cation pi interactions, for forming hydrogen bond interactions, for forming pi cation interactions, pi interactions, solvation, things like that. And for this example, I'm going to show you hydrogen bond here. So I'll just choose this thing here, which has 148 groups in it. And once I have chosen that, I can click on save here. And all I have to do is click on enumerate. And the good thing about ligand design is that when you launch this panel, when you click on analyze workspace, it automatically prepares a grid for your protein by selecting your ligand that is bound to it. So it has like some inbuilt mechanism of identifying where the ligand is bound to the protein and try to prepare a grid in the absence of the ligand for that protein binding pocket. And because you have built the grid in this particular option here, now you can see that when I click on the enumerate option, on the bottom, it says enumerating new ideas. So it has around 36, 37, 38 out of 148. And for those groups that it found to be successful to be able to fit in the binding pocket, it's going to give you molecules here that says like, 1, 2, 3, 4. Like you can see that so far out of 70 molecules, 72 molecules that have been tried, 16 of them were found to like fit in the binding pocket with some reasonable activity. We have to evaluate if those changes are good enough or not, but you can see that it's going to like, keep changing this molecule, and it's also going to dock these molecules automatically into the binding pocket, and it's going to tell you if the molecules are good or not. So for example, we got this results here. And so if I click on this particular molecule, that is one of the results from this ligand designer. Just hold on. Yeah. So if I click on this particular circle right now, now you can see that, okay, now you can see the change that happened in this cyclopropane group here. Okay. So the same way you can take a look at the other groups also. You can click on this particular circle. So you can see the changes that are happening in that region over there. And you can also see that sometimes it shows you that these atoms, like this group, is not going to be favorable because, let me just try changing. Yeah, you can see that it has like orange colored spheres here, which means it has bad clash with these atoms here. It's a bit close to those atoms. So things that can be found out easily with these options here. And you can just like see which all substitutes you are trying to check here, and if they can form interactions here. So how do you know if these changes are making the molecule better or worse? So if you go to the table here, you can again take a look at the docking score for all of these molecules, and it automatically shows you what the scores are going to be compared to your reference molecule. So the reference was minus 10.4. You can see that the other changes actually like made the molecule worse. And as I told you before, the molecule was already like very well optimized, so there wasn't much room for improvement. But I wanted to show you how you can use this tool to make it like slightly to find better molecules. And also don't be worried about these molecules that have score of 10,000. That's more like the software somehow tried to fit the molecule. But 10,000 is a very high docking score, so those molecules are not going to be appropriate anyways for interacting with your protein. So in this case, actually, I did not find any other molecule, any other fragment that can make the molecule better. But in your own projects, you might be able to like go for those optimization things that are going to happen. And for every change that it makes, you can see how the lipid skin rule of 5 is going to be affected for your molecules. And with that, I'll conclude this particular demo session. I hope it was clear to you. All you have to keep in mind is that you just have to like make sure you have a protein and ligand in the workspace, and then go to task, and then launch the ligand designer tool, and then click on analyze workspace. And that's going to give you all these options, and you can understand like how these things are going to be run. And for any reason, like you don't understand like how to use the tool, you can always like click on the question mark on the tool, and that's going to launch the menu, the whole manual for the software, where you can take a look at how to use that particular panel. And every panel has a question mark that you can just click on to find out how to use that particular panel in the best way possible. So thank you all for listening. I hope it was fruitful, and I'll hand over the session to Vinod. And thanks, Vinod, for sharing the handout. And with that, I'll conclude my demo.
Yeah, thank you, Kaushik, for helping us with that. So I think we shall wait for another 10 to 15 minutes so all of you can explore the ligand designer. It's an excellent tool, and let us know how you felt about it. So I shall wait for another 10 minutes so all of you can check and get back. Dear participants, I request you to follow the handout for ligand designer as explained by Dr. Kaushik. It's an exploratory thing. You don't have to follow the same protocol what is mentioned. You can explore, you can just identify what exactly you need, and accordingly you can design your molecule.